Welcome to CW Kids Ask. Today we are going to explore science, technology, engineering, and math, also known as STEM, in the historic trades here at Colonial Williamsburg. We have some activities that you may want to try as you watch. To do this, you will need a few supplies that you probably already have close by. 3 sheets of construction paper, a ruler, a pencil, scissors, tape, and clay or Play-Doh. Gather those things and we'll see you in just a minute.
Hello, I'm Davia Brown.
I'm Brandon Lyles.
And I'm Stacy Loveland, and we're excited to have you join us for Colonial Williamsburg's CW Kids Ask,
Where we dive deep into history.
Together, we'll explore 18th century life and connect it to present-day experiences.
We'll look at everything from fashion to science
And economy to archaeology. We'll take a closer look at our past and present.
Join us each month on our live streams and submit your own questions.
or watch past episodes and start your own conversations
The past has something for everyone.
So come join us.
as we discover the past. How do tradespeople at Colonial Williamsburg use science and math? Hello, everyone. Thank you all for joining us today for this episode of CW Kids Ask. This is our monthly live stream just for students, where we will explore 18th century life and learn about the people, events, and ideas that help shape America. Each month, we will bust some myths and misconceptions, explore primary sources, and answer questions that you send to us in the chat. I'm Stacy Loveland, and today we're going to answer the question, how do tradespeople at Colonial Williamsburg use science and math? Today, we are excited to be coming to you live from James Anderson's blacksmith shop here at the Public Armory. Joining me today, we have Master Blacksmith, Ken Schwartz, and Master Tinsmith, Steve DeLeo. Let's get started by having you each tell us a little bit about yourselves. Ken, I'll have you start.
Hi, I'm Ken Schwartz. I'm the master blacksmith for Colonial Williamsburg. I've been doing this work since I was a teenager 40 years ago. I started out working with a blacksmith. I ran a business for a little while. My interest was in historical work, so when I made connections at Colonial Williamsburg, this seemed like a natural place for me to end up as a career. So I've been here now for most of my career. In our shop, we research 18th century ironworking and decorative arts and technology, and then we recreate a work environment and use that environment to show, to make things that are used here within our historic area. So we work with iron and steel in this shop.
Fantastic. And Steve, how about you?
Steve DeLille, Master Tinsmith in the shop next door here in the Anderson Armory. I started as a tool and die maker. I've worked metal all my life, but I've always had an interest in history. And eventually, through a reenactment and trying to recreate objects that I needed for my own hobby, I developed the skill of reproducing objects based on research, 18th century objects. So always interested in making things by hand. So it's a combination of 2 interests, history and art, metalworking also. What we're doing as tinsmiths next door is transforming tin plate using pre-industrial methods to create objects that were used by soldiers and sailors of Virginia during the time of the War for Independence. And in fact, a lot of things that would have been very commonly used by everybody in the 18th century. So tin smithing, so working tin using pre-industrial methods.
Wonderful. Well, I am thrilled you were both here with us today. I know we're going to have a great conversation. For those of you watching, remember, send in any questions you have, post them in the chat. We're going to answer as many as possible. But to get us started, I actually have a question. Ken, we are in the blacksmith shop right now. Mm-hmm. What sort of work would we see being done here in the 18th century? What exactly are you doing today?
Okay, well, as I mentioned, we work with iron and steel. Iron and steel are really valued for their toughness, their strength, their durability, and their low cost. So iron and steel are used to make lots of common things. Parts for buildings, nails, hinges, locks and latches, furnishings for inside a building, tools for a fireplace, or tools for cooking or lighting devices, tools to get work done, tools for farming, parts for wagons and carts, and even some things like weather vanes for buildings here in town. And then as an armory, this shop also focused on work on weapons for soldiers. not the manufacture of weapons, but maintenance. So we were fixing muskets, pistols, swords, and bayonets, and providing other ironwork for soldiers.
Wow, so this is a really busy shop.
Absolutely.
Well, we have some great questions coming in. Rocco from Pocosin wants to know, what materials do blacksmiths use and where do they come from?
Well, our raw materials, the iron and steel, were products of local industries. So within the region of Williamsburg, there were a number of ironworks that mined iron ore and refined it into iron bar. So within 100 miles of our city, mostly near Richmond or Fredericksburg, there were iron furnaces that produced the bar iron that's our raw material. The other raw material that we need is coal, fuel for our fire. And just west of us, again near Richmond, there were huge coal deposits, and we used the coal that came out of the Richmond area.
Awesome. Autumn from Pocosin, Virginia, is curious to know what elements of STEM we're seeing used in this trade, and that's science, technology, engineering, math. Where's that popping up in blacksmithing?
Well, when you get into trades work and manufacture, you see STEM applications all over. So I would start with some of the mechanical elements of STEM, which would be, the hammers that we use, and you get some physics involved. With a hammer, the force that you deliver to the iron is a factor of the weight of the hammer and how fast it's moving. So when we do some iron work in a little while, you'll see that I'm swinging the hammer very fast and very hard. We use a lot of math in calculating a circumference of a wheel, for example, or any smaller circle that we need. We use a lot of measurements and dimensional measurements to figure out volume. That's true in a lot of the occupations also. And we have simple machines as part of our work as well, levers, screws, wedges, and you can see applications of those things in all the trade. And then finally, we have chemical reactions. So a chemical reaction would be our fire. We mentioned coal. Every fire has to have a fuel. Coal is our fuel. You have to have oxygen. You'll see that we're working a bellows that provides air to the fire. And then you have to have heat, which we get from a flint and steel to generate sparks. So maybe we can look at starting a fire.
Yeah, I was going to say, Callan from Pocosin has actually just written in about wanting to know how you start a fire in the blacksmith shop. And Callan, I'm thrilled you asked that question. Fire, as Ken just said, is a necessary element for blacksmiths, and it's a result of combustion. So yeah, let's take a look at how this chemical reaction works.
All right, so this morning we're going to look at starting a fire. And as we talk about fire, we'll remember that there are three components to fire. Sometimes it's referred to as the fire triangle. So you have heat, and that's what we'll start with. You got to have some sort of fuel, and then you have oxygen. So with those three components, you can get combustion. To get the heat in the 18th century without lighters or matches, you'd use a flint and steel. So this is a piece of flint. Flint is a naturally occurring stone that when it breaks with very sharp, jagged edges. And then with a piece of steel, if I strike the steel against that sharp edge, the sharp edge peels off little bits of the steel, and the friction of breaking them off makes them white hot. And so you get sparks, and you see the sparks from the flint and steel. So with my flint and steel, I'll take a little bit of the char cloth, and I'll set it right along the sharp edge of the flint. And the trick then is to get a spark to roll back and land on that char cloth. And maybe you can see there, I've got the char cloth burning. It just smolders. So now I'll wrap it up in this dried rope. And that gives me my flame, and then with the flame I can light a candle. All right, when we go to the larger fire, Let me move this out of the way and you can see what we've got here. In a blacksmith's forge, we have a pit where we build the fire, and we have a bellows that provides the oxygen. So you can see when I pull on the bellows, the air enters through this nozzle, and so I'll need to assemble the fire in front of that. I'll bring in my fuel, which is coal, and sort of surround it around that nozzle. Now, coal doesn't light easily. It takes a little accelerant, so I'm going to take some wood shavings here from our friends in the cabinet maker shop. I've also broken up some heavier kindling. So we're going from things that are easy to ignite but only produce a little bit of heat, the char cloth, now the candle. Now I'm going to take the candle flame and I'll transfer that to the wood shavings. You see they burn easily, but they'll burn up quickly. So to sustain that fire, I'll add some smaller kindling, just like building a campfire. You see how quickly the wood shavings catch fire. Add the kindling, and now push the coal in around that to start to contain the fire. And now we'll add a lot of oxygen, and that'll really take off. So you see how the bellows is adding the oxygen. As we start a fire, you'll also see that before the fire builds up heat, you get incomplete combustion. So that means you produce a lot of smoke. And as the fire gets hotter, you'll get more complete combustion. And that means we'll have more flame and less smoke. Another scientific principle that you notice is that hot air rises. And you hear how when that air blast stops, you don't get as vigorous combustion, so it doesn't make that same roar as it does when you're fanning it. So with some simple elements, with a flint, a steel, a little bit of char cloth, some kindling, and then coal as our fuel, that's the way we'd start the morning every day. We're applying the science of combustion to the work that we do here.
There are a number of chemical and physical changes that occur in the blacksmithing process. An important one is called thermal expansion. Ken, can you explain thermal expansion for our viewers?
Yeah, when you change the temperature of something, it changes the material. So one of the changes that occurs is, I'll use the heat of the fire to make the metal softer, but when it gets hot, it also gets bigger or longer. So you'll see that if I take a cold bar and heat it up, it gets longer.
And we have a video of you doing that the other day for us. So we can see it when it's cold, right? And then you heat it up.
If you look on the, if you look at your screen, you'll see that you tried a piece within a given space, and it fit easily. But when I heat it up and then try to fit it in that same space, it no longer fits, and that's because it's expanded due to the heat. See how that doesn't fit. And now if I cool that off in the water and take the heat out of it, return it to room temperature, the metal is going to return to its original length, and then it'll easily fit within that space once again.
It's amazing to have such a clear idea of how well that works, being able to see it so plainly there. Although looking at that, I think we're all realizing that the tools that are being used are going through a lot of wear and tear. And Emily from Percosin here is asking us how people are keeping their tools in shape in the 18th century.
Okay, well, for our tools, our biggest concern is when we're working with hot metal, if the tools begin to get hot, then the tools can change also, and they can get softer. But our tools really don't stay in contact with the metal long enough to get hot. So because the tools are room temperature, they're very, very hard. and the metal that we're working with is hot, so it's very soft.
Okay, so it's a nice balance.
Right.
Excellent. We're being asked now, how much material do you need to make a weapon for a soldier? Since we are, after all, as you both said, seeing our trade shops today set up as they were when this was an armory. Is that a pretty material heavy thing, making weapons?
Yeah, we pay close attention to the materials because when we're making something out of metal, the material is the biggest expense.
Yeah.
So we keep careful track of the metal. Now, the question about how much metal goes into a weapon, it really depends on the weapon. So if it's a small pistol, that takes a couple of pounds of metal. If you're working on a musket, that's a much larger weapon, or a sword, it'll take more metal. So the amount of metal you use depends on the weapon that you're working on.
That makes a lot of sense. Now, we have been looking at blacksmithing so far, but blacksmithing is only one of several trades being practiced here at the Public Armory. Also located at the Armory is a trade that is incredibly important to many people, including the military, and that's tinsmithing. Steve, can you tell us more about that trade?
Well, the trade is also in metalworking and iron, in fact, because what we start with are sheets of tin-plated iron. So everybody, even in the 18th century, will call this simply tin, what I'm holding here. By the way, the material we're starting with comes in sheets this size. This is the standard size for the period. And so it's a sheet of iron, and so some of the properties that Ken told us about iron apply for this. It's strong. It's also very cheap because it's the cheapest of the metals, the most abundant metal. But it's called tin because of this plating on the surface. So what I'm holding here is really a sandwich of metals. It's got iron in the middle, but what we see on the surface here, on both surfaces, is a layer of another element, another metal completely different called tin. And the reason we put tin on iron is because it keeps it from rusting. Tin doesn't oxidize the same way, so it's not affected by oxygen the same way that iron is to produce rust. And so because a lot of the things that we're making with this material relate to food preparation and food service, it's going to be a lot more pleasant to eat over a surface that's nice and shiny like that than on rusty metal. So that's why this material becomes very, very popular for a lot of objects, utensils, containers that are going to use in most people's kitchens. But for soldiers, it becomes invaluable because we're making cooking pots for them out of this.
Well, that's amazing. First of all, how many places we see that being used in the 18th century, but it also strikes me that if this is something being used primarily for cooking and food handling, it's going to be pretty important then that the things you make have measurable and consistent volumes, right?
Absolutely. In fact, I've got two objects here that are coming out of the armory from the same records that we have for the entire site here. We can extract a list of the objects that were being made, and these two objects are essentially the same thing, a cylinder with a bottom on them, but this is a 3-gallon kettle that is a cooking pot that's typical of what soldiers are using in the 18th century, and this is a measuring cup that's just half a cup, and often the soldiers are getting rations in this amount and then putting it in that kettle here and making their soup or stews every day. Okay. So these could be found in people's kitchens, but for soldiers, this here is important because everybody has to eat, even a soldier. And an army marches on its stomach if they have food, but also if they have kettles to cook that food in.
So that is incredibly important, like
Absolutely.
You said.
Yeah.
But how are you able then to calculate the volume? I mean, it's one thing to make something and measure afterwards how much water or soup you can fit in it, but how do you calculate it before it's fully made?
Well, there's different concepts here that relate to cylinders that are important. Of course, the volume, the 3 gallons is what it holds here, but that's all determined by the diameter of that container. So that the measure that's right across here, and half of that would be essentially a radius.
And you can see these displayed on your screen as well.
Yes, and the height, and all these measurements here can be worked through formulas to be able to calculate how much this will hold. So you can, from the start, just with numbers, be able to make patterns and aim for that amount that object will hold.
Fantastic.
And so that's very important to measure things because you don't want to waste material, but also you're trying to achieve specific volumes always.
Wonderful.
You have a goal that's measurable.
That's an excellent thing to be able to have if you're working on manufacturing all of that. Now, what's going to happen to the volume of the object you're making, that cylinder, if the height or diameter is adjusted?
Well, I just happen to have two other containers. One is called a porringer, so it's like a bowl with a handle on it. The other one's a mug, but these two objects hold the same volume. And the difference is that this diameter here and that diameter there are different, obviously, but it's compensated by the height. So actually, when you take all these measurements and you use a formula to calculate the volume, because of the different numbers, they all add up to the same amount inside. But so you can, something doesn't have to have a certain shape, to have a certain volume. It can vary as long as it all adds up to the amount that you have inside.
Well, that's awesome. We have some spectacular questions coming in from our viewers today. Do keep those coming. Keaton in Ohio has written in to ask us, we've been talking about tinsmithing, but we'd also started out talking about blacksmithing. So if we're talking about using fires, how much coal are we seeing specifically in the blacksmith shop, since they seem to be using a lot more heat than you guys? How much coal is a blacksmith going to use in a day?
Well, Keaton, we find in our experience, if we're working with the fire all day long, one fire would burn about a bushel basket of coal, or about 50 or 60 pounds of coal in a day. A day is regulated by the amount of sunshine we get. So we're getting into the time of year when the days are a little bit longer, we'll burn a little bit more coal.
Awesome. Thank you, Keaton. It's nice knowing we have questions coming in from everywhere, even Oklahoma. It's halfway across the country from us. So thanks, everyone, for tuning in and watching and writing in. If we are talking, though, about using heat in our trade shops here, obviously you guys are going through a lot of coal heating stuff up, but tin's heated up sometimes, too, both while you're working with it, but afterwards, too. If this is something you're using for cooking or even just eating, soup is warm. So how much does heating tin change its volume?
Well, it does change a little bit, but it's not as consequential heat for, well, you need heat for cooking. But since you're making soup or stew, that's not like a scientific experiment where you need absolute measures. So it's not a big deal. But when we're making these objects, we do use heat. We use heat, like the blacksmiths will use coal. We use charcoal, and you can see on the screen there that I'm soldering a seam on one of those vessels. So I'll use heat to solder. And soldering is the way that I have to glue these parts together. It's the same way I attach a handle, actually, that makes the seam, or make any of those seams tight so it doesn't leak. So I'm going to use a soldering iron that's heated in a small stove, and then pick up a tin alloy that's going to be applied in a liquid form because it's hot. But when it cools down, it goes back to solid, and the parts are going to be stuck together. So I do use heat in the fabrication of these objects, but my fuel is a little different because of the way, because I'm using a stove rather than an open forge.
That's really cool. Yeah. Now, I see you also have some paper with you on what looks like some pattern pieces.
Yes.
Can you explain to our viewers how to make the shapes that they're seeing here using their own paper that they got as our program began?
Well, this porringer here, that's a very useful object that shows up in our records, a bowl with a handle. The pattern we're using is a pattern that's made out of tin like that we can trace. So we'll use a pattern like that we'll trace directly on tin and then cut and form over a stake. And in other words, it's flat like that, but then when you bend it over a kind of a specialized anvil to be able to get the form, and you can see that on the screen also, you're going to end up attaching both ends here to make that cylinder. But our patterns, when they start, are actually made of paper, because that's the easiest way to start with a pattern. And so, because when you're developing these, sometimes you can be off a little bit, so you can adjust a lot easier on paper than on metal. So this disc here will correspond to the bottom, and this rectangle here actually becomes the body. So the body is bent around, and then it's going to be attached on both ends like that to produce that cylinder. And then, once we have these two parts together, we can attach them to make that container. So That's how we figure out the patterns, and then when we're really sure about that, then we'll make it into a tin pattern that's going to last a lot longer than paper.
So, and using your own papers today, you can try that out. If you take the long edge of one paper, as Steve just showed us, that becomes the circumference of your circle. So you can use all the equations we showed you earlier for circumference and diameter to circumference and diameter to work backwards.
Yeah, the circumference is that measure
out.
all around, but it becomes a straight measure here because if you take this and you roll all around, see this is the half measure there, but then it goes back to the original point over there when you get all around to this end. So that measure around is the cylindrical measure for this one here. So the circumference corresponds to the length of this. So, yep, we use these concepts of circumference, height, width, radius, diameter. All those are numbers that are important for us for making these cylinders.
Awesome. Now, Emily has written in with a great question, wanting to know how they're measuring height in the 18th century.
Well, very simply, this way. So the height is that measure here. So you would simply take a ruler and measure here, and this one is 5 inches.
Awesome. So you're using inches, and you have a nice ruler
Yeah.
already to help you in
Well,
the shop.
what's interesting is that we're using inches just like in the 18th century, but what's also interesting is that the standard measures that we're using for the volume, like the ounces and gallons and all that, are the same as we're using during colonial time today.
That's really cool. I love when things stay the same across time. Neat to have those connections to the past. Now, as I'm looking around the shop that we're in today, here in the blacksmith shop, I'm seeing many items that would be classified as simple machines. Simple machines, as Ken already mentioned, are going to include things here like planes, screws, wedges, wheels and axles, levers, pulleys, and I really, in particular, want to know all about this pulley that you have set up and how it's actually going to work. Can we test that out?
Yeah, so any simple machine gives you some sort of mechanical advantage. So it makes you seem stronger than you are. You have to apply less pressure, less effort to move something. In this case, we have 2 pulleys, top and bottom, and each of those pulleys has an axle with 2 wheels on it. And then we have a rope, you see, runs here through one wheel, then up over another wheel, then through another wheel, then back up and attaches to that pulley. And by running the rope through several pulleys like that, wheels like that, it makes it much easier to lift something. So as an example, I've got a small anvil here that I'll move without the benefit of a pulley. And you can see, you know, anvils are pretty heavy things. So I have to
Out of your way.
lift it and walk it across the room to put it on the table. But we have another anvil identical to that one that's attached to the pulley. And you can see Stacy's able to lift that anvil with a lot less effort because of the mechanical advantage of the pulley. So pulleys make some work a lot easier.
Yeah, I don't think I could have lifted it without the pulley. That's really cool. Well, we are still getting some fantastic questions. Thank you all for writing in. Madison, seeing how many things are in the shop, wants to know how many items are being made in a day. And I'm going to ask each of you to answer that.
Well, it can vary depending on the size and the complexity of the object. The simplest thing we make here would be nails. There were a lot of nails made during the war. And one person who's practiced at making nails could make almost 1,000 nails a day.
Wow.
But then something that's much more complex, like a door lock or parts for a musket, it might take all day or even more than a day to make a single object. So it varies with the work and the skill of the worker.
That makes a lot of sense. Steve, what about in your shop?
Well, I've got 2 examples here of objects that are coming out of the shop. And I can make this in 3.5 hours and this in half an hour. Now, it depends again on the kind of orders we're getting. If somebody's getting this with several of those cups, or if they're getting several pots or other objects that can take a day to make that are more complicated, then it varies enormously. So we can't say, we say we're working all day, but we can't say how many units of objects we're making.
And I'm sure some of it depends just on the orders.
Yeah.
that
Also,
are
in a
being
day,
used
a
too.
day is different in the summer and the winter.
That's a
Days
very
are
good
longer
point.
because you've got a lot more sunlight. So you can work and be more productive in the summer and less in the winter.
That's a really good
You have to
point.
take that into account too.
Thank you for that.
Yeah.
Now we talked a lot about the materials blacksmiths go through, how much material is used in different things, how much coal they're using. But what about tin? Sierra wants to know how much tin a tin shop is going through in a week.
Again, it really depends on the objects that you're making. An object like this here, this large camp kettle, is a good example of to show you how much tin goes into an object like that. I need 2 sheets here on the sides. I've got a seam here. This the bottom is made into another sheet, and what's left over creates this. So 3 sheets to make one of those, and I'll make one of those in about 2 hours. So I can make 4 or 5 in a normal day. So you have to multiply 4 or 5 by 3 sheets, and that would be the amount of sheets that you're going through.
Wow,
That's to give an example.
that's going to be a lot of tin if you have big projects coming through.
Yeah, it's always a multiple or a fraction of a sheet like what I was holding because you don't want to waste.
Of course.
And so you're trying to maximize the use of that material.
Well, speaking of maximizing the use of our material, Abby is asking, are they recycling the metal that's being used in the 18th century? I mean, we hear a lot about recycling today. Are they doing that in the 18th century too?
You can go ahead.
Yeah, certainly in iron and steel work, we can recapture the metal easily and reuse it. In fact, one of the things we offer our customers is credit on their accounts for bringing us old, worn out things or scrap. So recycling is important for economic reasons in our day.
Unfortunately, in our case, our material, once it's been made into an object, it loses its intrinsic value, meaning that you can't put it on a scale and say, wow, I've got so many pounds of tin and it's worth that. The problem is that it's tin on iron, and to be able to reclaim it, you would have to be able to separate the 2 metals efficiently, and we don't have that technology in the 18th century. It's going to be developed much later. Today, yes, tin from tin cans and all that is recycled, but we don't have that. And that's one of the reasons we're using very efficient patterns, so we don't waste the material, because we really can't recycle our scrap.
That's really neat. 2 very different answers, but both metalworking trades. Thanks for that. That was a great question. It's not just the metalworking trades, though, that are using STEM, and it's not just the metalworking trades that are being efficient with what they do. You can find examples in every single one of our historic trades, and the milliners and mantua makers in particular are using geometry every single day. Apprentice Kate is now going to be able to teach you how to make a child's shirt using basic geometry.
Hi, I am Kate, and I am the apprentice to the milliner and the mantua maker here at Colonial Williamsburg. As tradespeople in the 18th century, we're always concerned with making sure that we're using the materials to the best of our ability without any kind of waste, because fabric can be really expensive in the 18th century. As milliners, then the way we're trying to make sure to avoid as much waste as possible is by working using basic geometric shapes, knowing that I can take a rectangle of fabric or of paper and create all kinds of garments. The handkerchief that I'm wearing around my neck, it's the same kind as this one here, and this is just a square of fabric which I folded like a triangle. If I don't even have enough fabric for that square, I can just cut a triangle, hem the edges, and lo and behold, I have a garment that I can wear. The apron that I'm wearing, the apron that I have right here, is just a couple of rectangles sewn together. My apron has one large rectangle and then a small rectangle for the ruffle. This apron is made of 2 rectangles that have been stitched together right down the middle. Now, the garment that I'm going to show you guys how to make today, this child's shirt, that's just made using a rectangle of fabric. Or in the case of this project, paper, which you guys should have with you, as well as your scissors, your ruler, and a pencil. So we're going to start by taking the fabric and folding it twice. Once kind of hamburger style, once hot dog style. And when I fold it, I'm making sure that I'm taking the edge of the paper and creasing it so that those lines are going to be visible even when I've unfolded it. So I'm going to take that, I'm going to stretch it out here. And my next step is going to be taking my ruler and measuring 3 inches down. These are going to end up being the sleeves for the garment. So I'm just going to fold it again right there. Then I'm going to take my scissors and cut along that fold to the first of kind of the creased marks that I've made on the paper. So already you guys can see that this is starting to look a lot like a shirt. Next step for me is going to be taking my scissors, and I'm just going to open this up again, and cutting up that creased line right in the center. And here's where we're going to get our ruler out, and we're going to make just a couple of measurements. We're going to measure 2 inches from that cut out line here, and then we're going to measure 1.5 inches, so halfway down that kind of tube for the sleeve. I'm just going to take my pencil and kind of draw that curve out, and then I'm just going to take my scissors and cut around that curve. Now, to save a little bit of time, I could have taken my pencil and marked out the curve on the other end, but here I can just fold it over, and then I have a template. Here I have a pattern that I can cut around. Now, if I were doing this in fabric, I would then just take a couple of my basic stitches to construct this garment, to put it together. And here that would just be a back stitch and a hem stitch. Or because this is paper, I can just take some tape and assemble it. And there, I've made a child's shirt with only this little oval of fabric left over. Now, if I were making this bigger, if I were making an adult shirt or a shift, this kind of semicircle could go ahead and become the crown for the cap that I'm wearing, or maybe the gussets, the little square inserts that are going to go in the sleeves of a garment, or this can just go in my scrap basket for me to use for another project later.
How did your shirt turn out? I think mine looks pretty good. In fact, I think if it were made out of linen, I could be able to sell it and make some extra money. And an important part of any trade is money. I mean, it's something we all need to have to pay for goods and services, and the master of any shop is going to have to know mathematics in order to balance his books. Seeing what money customers have already paid and what money is still owed helps the master plan and also pay his free workers. For this month, our primary source comes from James Anderson's account books. There are some things that you're going to need to understand, though, when talking about money in colonial Virginia. People often use different types of currency, such as pounds of tobacco and pounds, shillings, and pence, when talking about currency. For our purposes today, we are going to use pounds, shillings, and pence. Pounds are the larger sum of money, shillings are smaller, and pence are even smaller than that. Now, for this exercise, you need to know that there are 12 pence in a shilling and 20 shillings in a pound. It's a bit complicated, right? But don't worry, I am here to help you make sense of it. Let's use an example from James Anderson's account book to better understand the math. Here is what he is charging Daniel Prentice. Now, you can see the numbers on the right. The first number is the pounds, the second number is shillings, and the third number is pence. So the amount on the first line is 1 pound, 10 shillings, and 0 pence. The second line is 0 pounds, 12 shillings, and 6 pence. Let's add them together to see what Mr. Prentice owes to Mr. Anderson. Start by adding the pence column. 0 plus 6 is 6, then shillings. 10 plus 12 is 22. If we know that there are 20 shillings in a pound, then we can carry 1 over to the pound column. This would leave us with 2 shillings. Finally, we have 1 pound plus the 1 pound we carried over, and this would give us 2 pounds, 2 shillings, and 6 pence. Now let's look at another example. Here is Richard Charlton's account with Mr. Anderson. Start by adding the pence column. 9 plus 6 plus 3 plus 9 plus 9 equals 36. If there are 12 pence in a shilling, 36 pence is actually 3 shillings. So let's put that 3 into the shillings column. And because there are 0 pence left over, we will leave that column with a 0. Now let's add the shillings. 18 plus 12 plus 8 plus 1 plus 7 plus 2 plus the 3 that we carried over equals 51. Because there are 20 shillings in a pound, we can take 40 out of that 51 and make 2 pounds to carry over. We still have 11 shillings left over, so we put that in the total of the shillings column. Finally, we add the pounds column. 4 plus 5 plus 1 plus 1 plus 3 plus 15 plus the 2 that we carried over equals 31. 31 is placed in the pounds column. This means that Mr. Charlton owes Mr. Anderson 31 pounds, 11 shillings, and 0 pence. Now let's see how well you do on your own. Try adding just the first 4 lines from Mr. Taswell's account. 4 pounds plus 5 pounds 5 shillings plus 3 pounds 12 shillings plus 18 shillings 3 pence. Once again, that's 4 pounds plus 5 pounds 5 shillings plus 3 pounds 12 shillings plus 18 shillings 3 pence. If you think you have the answer, post it in the chat box. We'll give you the correct answer at the end of the program. Now we have some more fantastic questions coming in from our viewers today. Brian is asking us something that corresponds perfectly with our primary source. Thank you, Brian. How much did someone have to pay for work done in a blacksmith shop? Can you give us a better idea of that? We just heard a lot of numbers, so what do we expect?
Yeah, so the way we figure the prices on the things that we make is by the amount of material that gets used. So a finished product would be put on a scale and we would weigh it, and you're charged usually about 9 pence per pound for the finished iron. And what that tells you is that the material is more valuable than the workman's skill. You know, the material is more expensive than the labor that makes something. So we charge according to the weight.
Wow, that's really cool. And makes sense why we see so much variation as well. Well, now that we have bent our brains doing some math, let's bend some metal and talk about malleability. Something that is malleable is something that is capable of being shaped, as by hammering or rolling. If you have your clay or your Play-Doh, you'll want to bring that out now. Can you show us an example of how things become malleable in your shop?
Absolutely. We start, our raw material would be bars of iron like this one. And you can see at room temperature, if I come over to the anvil and hit that, that bar of iron's pretty tough and it won't change shape. So we talked about fire earlier. I'm going to go to the fire. And if I give it air, that will raise the temperature. And I can use the fire to heat the iron. When the iron is heated, it gets softer, so it takes on properties just like modeling clay. So you'll be able to try to replicate some of this shaping with the clay that you might have. I'll judge the temperature by color. So I want a temperature that's a yellow hot here. When it's yellow hot, I'll be able to go to the anvil and do the shaping. But I'll have to act quickly because the metal doesn't stay hot for very long. So as I get up to yellow hot, I'll initially do the shaping by turning the metal back and forth under the hammer. And as I do that, it makes it narrower and thinner and stretches it out in length. So just like clay, when I shape, I'm not changing the volume. I have the same amount of metal, but I'll just change the shape. And then I'm going to do some bending. So I'll bend the end down around and then bring it back towards me to make a small loop. And for this project, the loop just keeps us from having a sharp point on the end. And then I don't want to change that loop, so I'm going to cool that briefly in water. And I'll do another bend here using the horn of the anvil and bring that around to form a hook. So I've formed a hook. I formed the one end of the hook using the combination of stretching and bending. And now we want to make one last change to the hook to add a little ornament to it. And this is something else that you can do with the clay. I have to heat up the middle part of this hook. Again, I'll heat it up to that sort of yellow color where it makes the material very, very soft. And then to add an ornament, I'm going to twist the hook. So let's look at how twisting is done and what the result of a twist would be. It takes a minute for this to heat up, so I'll watch carefully, watching the temperature while I'm fanning the fire. So almost there.
And if you've made your hook with clay so far, you might want to make sure that the edges are square at this point so you can twist it too.
All right, so now I have the heat. I'll bring it out of the fire, and I'm going to grab it with 2 sets of tongs, and I can use those tongs, use the leverage of the tongs to twist that right around and make an ornament in the middle. Let me make sure this is straight. And then you can see perhaps how the change has occurred right here to make that ornament. Here's what the original bar looked like, and you see that twist. So it's a very simple way to ornament the piece. And it's impressive to many people because most people are used to encountering iron when it's very, very tough. But you see the heat makes it soft and malleable.
That's really neat to be able to see. How did your hooks turn out? Hopefully they look something like that, although I think your metal one's probably going to be a little stronger than our clay ones. Now, each month we have the opportunity to explore some common myths related to our topic. Ken, are there any myths about blacksmithing that you would like to bust for us today?
We encounter a few things, myths, or I like to call them myth conceptions. And it comes from people's experience. At the sort of end of the time when blacksmiths were common, one of the most common jobs they had was shoeing horses. So we get a lot of questions about whether we shoe horses. The other question comes from modern entertainment world and television that portrays blacksmiths as sword makers. Well, making horseshoes and making swords would be part of the trade, but usually those were specialties. So a horseshoer would be called a farrier, and a sword maker would be called a sword cutler or a sword smith. It's not to say that a blacksmith never did that sort of work, but a blacksmith usually is doing custom manufacture and repair, and then people that are manufacturing common things specialize in their work.
Well, you guys already are making so much. You clearly have your hands full and don't need to take on the work of a farrier on top of that too. This has been a wonderful program, a wonderful conversation. Thank you guys for joining us, and thank all of you so much for joining us for today's episode of CW Kids Ask and for sending in so many awesome questions. We encourage you to find out more about STEM and the historic trades in the 18th century by either visiting us here in person or by viewing the links on our website. And the answer to the math question about Mr. Taswell's account, for those of you wondering, is 13 pounds, 15 shillings, and 3 pence. Congratulations if you figured it out. The program today is sponsored in part by a generous grant from the National Endowment for the Humanities. Thank you, Ken and Steve, for joining us today for this excellent conversation and this look into STEM. And for all of you out there, don't forget to watch our next episode on May 18th, when we'll ask the question, how does archaeology teach us about history? Until then, have a great day.